Hello, I am Gabriel from Group 26 and we will go through a simple RISC style CPU simulation, which is written in a C++ program by our group. And in this video, we will cover how it works and what each part does and what output we would expect. And this is the library that we use in our program here. And right after that, we will see the CPU components used, which contains the program counter, the instruction register, the register, and the memory. This program also includes a small instruction set, which is the load, store, add, sub, jump, and halt. Besides that, it also contains the memory, which is represented as a 64 element array. All right, let's begin from the main function. And here we initialize our CPU. The main function contains the four general purpose register, which is R0, R1, R2, and R3. We set all the register from R0 to R3 to 0 and preload the memory address 10 and 11 with the values of 5 and 7. Then we define a list of instructions just like a program that the CPU will run step by step. For example, load R0 10. And this factor and right over here is where we fetch the code and fetch the instruction, which is a while loop. And in this while loop, it will fetch the instruction such as a simple string like load R010, and it will use the instruction for the program vector using the current value of the program counter and stores it in the instruction register. And right after that, the instruction in the instruction register is passed to the decode execute function, which handles the parsing and execution based on the instruction type, which is right up here. And over here, you will see that the decode execute split the instruction into parts, which is the opcode and the operands. And each if else statement is a block which matches a specific instruction. And this one, it loads a value from the memory address into a register. And the store, it stores a register value back into memory. And add, it adds two register values and stores the result in another register. And sub, which subtracts the second register from the first and stores it in the destination. And jump, which jumps to another instruction index by changing the program counter. And halt, which immediately ends the CPU run loop. We also have a else statement which will detect if the instruction is invalid, and it will show an error which prints out unknown instruction. And right after that, right after the decoding part, right after the instruction is executed, the current state of the CPU is displayed, including the values of the PC, IR, and the 4 registers, which is done by the print state function. Okay. Besides all the talk, we should also see how the program shows its outputs, which is right here. As you can see here, the program counter is 0, and the first instruction register, it asks to load the register R0 into the memory address 10, which this is the current register which contains 0 value. And after that, after it loads the R0 from memory 10, which is 5, the program counter will increment by 1, and the next instruction register will continue, which is after this, let's load R111. And you can see from the output, it follows the instruction correctly. And after the halt, which is over here, halt encounter, the CPU loop is stopped. And this is the final output, which shows that the final memory states from address 0 to 13. And correctly, the memory address from 10 shows 5 and 11 shows 7. 12 came from the add instruction set, which is it adds the value from R0 and R1, which is 6 and 7, which is 12, and stores it in the memory 12. So yeah, this simulation may look simple, but it's a great starting point to understand how real CPUs work under the hood. So that's all for our video demonstration from Group 26, and thank you for watching.
Okay, today I would like to do a demonstration and explanation about our custom coding in cache simulation. Okay, first, here is our coding for the custom cache simulation in C++. Today I will just walk through this coding first and then do the simulation. Okay. First here, the goal of our coding is to simulate how different the cache configuration and replacement policies, namely like LRU, FIFO, and random, affecting the memory access performance during a typical computational test like matrix multiplication, which what we use in our cache simulation. This coding also supports set associative cache design, configurable cache size, block size, and associativity. A runtime program report show hit or misses rate and execution time. Okay, let's see our coding here. The program begins by defining the basic data structure. For cache simulation, we have here the cache line structure, which represent a single block in a cache set. Then each line stores its tag, whatever it's valid at the last use time, the inserted at time for replacement tracking. Then we have cache set structure here, which contain a vector cache line entries depending on associativity. Next here we see the cache class is where most of the logic happens. During initialization, the program calculates how many sets are needed using, where's the formula? This formula. Num set equal to total lines over associative, which is the total lines is equal to cache size over block size. Each cache set is then initialized with the appropriate number of lines. When an address is accessed using the access function, the program calculates the block number, the set of index using modulo, and tag using division. If the tag is found in valid within the correct set, each cache hit. If not, it a miss. And the program determines whether the line to be placed based on the selective policies. Okay, next we take a look in replacement policies here. Where it is? Okay, replacement policies. What we use here is LRU, FIFO, and random, which is simply pick a line at random to replace in here. And then we see next is, let's talk about cache simulation, where the cache simulation is applied, which is this part of coding that apply matrix multiplication. Okay, this is where it happens. Cache access address A, cache access address B. Okay, let's talk about where the catch simulation is applied. It's happened inside the matrix multiply function, which is right over here. And then we can see this is where it is applied. Catch access address A, catch access address B, and catch access address C. They simulate memory access from matrix A, B, and C. Each address is calculated based on base memory offset and index values using this formula: address equal to base A plus I times matrix size plus K times word size. This address represents how to fetch in row major order during matrix multiplication. Okay, so next is our main function lah, where the users allowed to configure it and insert the value. Okay, here function allows user to configure catch size, block size, associativity, and replacement policies. Once matrix is initialized, the multiplications runs with timing measured using clock function. After execution, we get a performance report with total access, number of hits and miss rates, and execution time in milliseconds. Okay, so let's demonstrate the code. I will compile and run. Okay, here we can see the interface of our coding catch simulation. Okay, so we can enter the catch size. We use 4 kilobyte, but we already set the parameter, which is 4096, so we use that. And then a block size of 16, associative of 2, and replacement policies 0, which is the LR view. Okay, here we receive a report. As shown, the hit rate depends on how well the access pattern aligns with our catch configuration. Okay, so that's all from me for the demonstration and explanation about our code. Thank you.